Bismillahirrahmanirrahim. Assalamualaikum. In this video, I will demonstrate to you the difference between the branch, subroutine, and interrupt. Yep. Okay. On our previous video, we already discussed, I already explained about the difference between these three branch, subroutine, and interrupt. But in this video, we will see a little bit detail on the difference between three of these. Okay, so I write this coding here, starting from here until here. Okay, as usual, we will need to build a file to make sure that our coding is free from error. Okay, it's zero error, zero warnings, and then we run the debug. Okay, here's the program. We run. Now we found B, meaning that branch without a condition, meaning that branch without BEQ. For BEQ, branch if equal to 0, but in this case branch always branch, or we can use, instead of B, we can use BAL, branch always. Yeah, so definitely when I click this button, microP will take this branch because we instruct microP to always branch. MicroP will skip this instruction at line number 105, 106, 107, and branch to skip here. Okay, watch it carefully. 1, 2, 3. Okay, next we run again a program, arithmetic shift right. Okay, and now branch. Here is called a branch to subroutine. The instruction that we use is BL, branch link, meaning that we link our main program with this subroutine. This is subroutine 1 is just a label or a name for the subroutine. You can name it as any name that you like. Okay, so the purpose is to link this main program with this subroutine program, and so that microP know when it finish execute this subroutine program, it need to return back to the main program. That's what we call link. BL, branch and link. We link this program, this subroutine program, with the main program. Okay, so let us see what happened. Branch link, microP will branch to subroutine 1 here. So at this moment, microP will skip execute instruction at line number 112 until 118. Okay, in 3, 2, 1. Okay, microP go to subroutine 1 and start execute line by line all instruction under subroutine 1. Okay, execute line number 121, 122, 123, 24, 25, 26, 27, and now it found BXLR. This BXLR is mean branch and exchange. Exchange to where? To link register. Here, LR, link register. Okay, here is a subroutine program, line number 1, 2, 3 until the end. When we want to return to the main program, we must use instruction BXLR, branch exchange to the link register. And then after I execute this instruction, microP will return back to, in this case, microP will return back to here. Okay, soon before next instruction that micro P not yet execute previously. In this coding here at line number 112, micro P will return back to here to execute this line because micro P not yet execute this line before, right? Okay, in 3, 2, 1, see, micro P go back here, meaning that micro P go to execute subroutine program. After finish execute subroutine program, micro P will return back to execute a main program. This is a main program and this is subroutine program. Okay, micro P continue, execute, execute, and execute again, execute, execute. Okay, now SVC is not a normal instruction. It is referred to a supervisory call instruction. SVC is stand for supervisory call. Supervisory call is fall under interrupt, one of the type of interrupts. Because like I mentioned to you on our previous video, there are various type of interrupt. Here we got normal interrupt, system tick, PENDSV, SVC, hard fault, NMI, reset, and etc. So SVC is one of the interrupt. Okay, so let's see what happened when micro P execute interrupt. When micro P execute interrupt, micro P will jump to the, in this case I named the interrupt service routine program as SVC handler. Yeah, but this SVC handler is a interrupt service routine program like this one. This is an interrupt service routine program for SVC. And then micro P will execute this program. After finish execute the program, micro P will return back to the main program. But there is a lot of difference between the subroutine program and interrupt service routine program. Okay, let's see here. For interrupt service routine program, before micro P jump or branch to execute this SVC handler, micro P will store to memory a few value of this register. Here in this our programming model, there is a data 1, 2, 3, 4 data that we use on our main program. When we execute our main program and subroutine program, there is already data here, and this data may be usable by the main program. Okay, so before micro P start to execute the subroutine program, micro P will store a few register content here into the stack. So remember what is stack and where is stack. What is stack and where is the stack? Okay, where is the stack is pointed by the stack pointer, meaning that this stack pointer is point to the stack address. In this case, address 2000 1000. Here at the memory, at address 2000 1000 refer to this byte, right? Exactly this byte, and this stack is referred to a temporary memory that is used by the micro P to store temporary data. Okay, the data is not permanent inside this memory because after when we turn off the system, the data will be lost. And the importance of this stack is useful for the micro P to store this data temporarily. Okay, so which data will be pushed to stack? when micro P want to execute this interrupt. The register that involved is here. Register PSR, XPSR, here, add PSR, PC, program counter, link register, R12, here, XPSR, PC, LR, but not stack pointer. R12, yes, will be pushed to stack, and then R3, R2, R1, and R0, here. PC, LR, R12, R3, R2, R1, and R0. The content inside all these registers will be pushed to stack. Why? Why micro P push all this register value into stack? It is to make sure that the data, the useful data for the main program is not overwritten by a new data when micro P execute this SVC handler. So we consider that this is all the important register, normally important register for the main program, so that main program main program need to use again this data when when the micro P return back from this SVC handler. Here, when micro P finish execute this SVC handler and return to the main program, micro P need to use again the original data. Okay, so let's look here. Here it is stack pointer, meaning that stack is start here. So I will execute this instruction. One, two, three. Okay, you see now? Before this, the data here is all filled with 0. But now you can see the data here. So where's the data came from? From here, XPSR. Okay, before this, you suppose need to record the previous data before we click the this button. Meaning that before we jump to run the interrupt. So this the value for previous XPSR value, and this is the data for previous PC program counter, and this is the the data for previous link register, and this is the data for R12. You compare data here, 5, 5, 6, 6, 7, 7, 8, 8. Here, 5, 5, 6, 6, 7, 7, and 8. R12, R3, R2, R1, and R0. Yeah? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And now we can say that the data at this 8th register has been copied to the temporary store. Okay, we already back up the data to the storage, and now inside this SVC handler, we can use this 8th register to execute a new set of program. What happened to R4 until R7? It is not automatically pushed by the interrupt instruction. If we think that the data is important to us, we need to manually push this register content into the stack by using push instruction. Here, in this example, I push register R4 and R7 value, R4 until R7, meaning that R4, R5, R6, and R7 value to stack. Watch that. The stack pointer now, previously the value for stack pointer is 2000, 1000. But now the new value for a stack pointer is 2000 0F E0. 0F E0 meaning that here is referred to here. Next data that if I instruct the microP to push or to save or to store a new data, microP will not overwrite to this original data, to this previous data, but instead microP will write at this line starting from FFE0, it minus with 1, and then write at the new location. Okay, let's see. In 3, 2, 1, stop. Okay, FE 800048 here. FE 800048. Remember, microP will push data from bottom here until here. Starting from previously, when we execute interrupt, it will start with XPSR, followed by PC, LR, R12, 3, R2, R1, R0. In this case, it will start push R7, R7, R6, R5, and R4. Here is for R4, BA, DA, AD, AA. Here, BA, DA, AD, AA. From R7, R6, R5, R4. Okay? Okay. So if you notice that all this data is stored in the form of stack, one after one, like this one. One after one. Here. Starting from original SP, it start at address 2000, 1000. When I instruct the first register that microP push just now is XPSR, starting from byte 1, byte 2, byte 3, and byte 4. Like this one, byte 1, because the size of the XPSR register is 32 bits. One address only store 1 byte. So for byte number 1, byte number 2, byte number 3, and byte number 4, it starts with byte number 1, and then microP stack pointer will minus by 1. 2000, 1000 minus 1 is 2000 0FFFF. It used to store byte number 1. And then it minus again by another one. So it store B2, B3, and B4. So the new SP stack pointer value after microP finish push XPSR will be SP minus 4 or equal to 2000 FFFC. Okay, to make it easier for us to discuss about this issue, I just group here for memory. Instead of I use 1 byte, I use 1 word. Okay, starting from SP minus 4. Yeah, SP minus 4 minus another 4 or SP minus 8 here. Okay, so this address 0FFC is used to store XPSR. Okay, let's see here. 0FFC here. FC, FD, FE, FF, 10. So here is used to store XPSR, and here used to store PC. Here from FFF8, FFF9, FFFA, FFFB. Here FFF8, FFF9, FFFA, FFB used to store PC, followed by link register R12, R3, R2, R1, R0. And this part is happen automatically when micro P execute interrupt instruction. But on my example, I manually push using a push instruction. I manually push R7 until R4 or R4 until R7, starting from R7, R6, R5, R4. Okay, this one is I push manually. Use different instruction. But for this yellow one, it happen automatic. Okay, so if you notice that, what is the current value for SP? Okay, here is SP minus 0 minus 24 minus 24 minus 24 minus 2 8 minus 2 C, and here minus 0. So the final content will be D, C, D8, D4, and D0. Okay, so the current SP value will be 2000 0F D0. Okay, let's see it on our simulator. Here, 2000 0F D0, meaning that if we write another push instruction, micro P will store the value into this here. Starting from atas ni lah. Here. Okay. So guys, hopefully you understand how this stack instructions work. Okay, let us try to run this SVC program. This program is run execute under the PSR, under the what we call it, interrupt, under the interrupt mode. And you can see here under interrupt service routine ISR, micropin node here is changed. Before this the value is 00, but now the value is 11 to indicate that this is the interrupt number. It's referred to the interrupt number. SVC ni is interrupt number is represent here. We look in detail after this into this next. So we execute again. We execute load. Okay. Remember, before this, I manually push the register value of R7, R4 until R7 to stack, and now to call back or to store back the value to the program model, to the model or to the register, we need to instruction of pop, or for certain processor it use instruction pull, but for ARM it use pop. Pop the value from stack here 1 2 3 4 and put it to register number 4 5 6 7. Okay, so let's see what happened. 1 2 3 up. So the original value BADAADAA 1 2 3 4 CD will be restored back to the previous register number. Next, after we branch exchange, please record this value before you execute this one. This value EFFDDEDE is the value that we update inside this interrupt handler, interrupt service routine handler. Yeah. So before microP return back to the main program, microP need its original data at programming on its programming model, so that it can continue execute whatever it is execute before the interrupt happen. Okay, so when we execute bxlr, okay, watch it up, microP will reinstall the all this value, will copy back all this value to its original location here, and the stack pointer value is returned back to the original value to 2000 1000. How do the microP know? MicroP read back the value from here. Yeah, stack pointer, microP will decrease back before this. Sorry, will increase back before this. MicroP decrease by 4 by 4 by 4. So microP will, when I use a pop, microP will increase this. Will restore this value, and then stack pointer value will be increased to 20, and then bxlr will restore this register value, and then the original stack pointer 2000 1000 will be restored back to SP register. Okay, so I believe that it is quite confusing for you, so you need to spend a time to understand this, and then we will discuss on our group. And the most important thing that you need to understand at this moment is the process. What is the process when the subroutine is being called by the main program, and what is the process when the interrupt service routine, like this one. This is only the example. For one example for interrupt service routine, when microP execute the SVC interrupt service routine. Okay,